Hey guys, how's it going? Let me continue with the book on page 100. One common use of pointer arguments is in functions that must return more than a single value. You may say that swap returns two values. The new values of its arguments is an example. Consider a function getInt, which performs free format input conversion by breaking a stream of characters into integer values. One integer per call, getInt have to return the value it found, or an end of file signal when there is no more input. These values have to be returned as separate objects, for no matter what value is used for EOF, that could also be the value of an input integer. One solution, which is based on the input function scanf that we will describe in Chapter 7. It is to have getInt return EOF as its function value if it found end of file. Any other returned value signals a normal integer. The numeric value of the integer it found is returned through an argument, which must be a pointer to an integer. This organization separates end of file status from numeric values. The following loop fills an array with integers by calls to getInt, like this code. Each call sets v to the next integer found in the input. Notice that it is essential to write $v instead of v as an argument of getInt. Using plain v is likely to cause an addressing error, since getInt believes it has been handed a valid pointer. getInt itself is an obvious modification of the A to I we wrote earlier. Throughout getInt, Strcmp is used as an ordinary int variable. We have also used sketch and ngedge described in Chapter 4. So the one extra character that must be read can be pushed back onto the input. Exercise 5, middle score 1, write getFloat, the floating point analog of getInt. What type does getFloat return as its function value? 5.3 Pointers in arrays. In C, there is a strong relationship between pointers in arrays, strong enough that pointers in arrays really should be treated simultaneously. Any operation which can be achieved by array subscripting can also be done with pointers. The pointer version will in general be faster, but at least to the uninitiated somewhat harder to grasp immediately. The declaration defines an array A of size 10. That is a block of 10 consecutive That is a block of 10 consecutive objects named A break it 0, A break it 1 till A break it 9. The notation A break it I means the element of the array I positions from the beginning. If PA is a pointer to an integer declared as int asterisk PA, then the assignment sets PA to point to the zeroth element of A. That is, PA contains the address of A break it 0. Now the assignment x equal asterisk PA will copy the contents of A break it 0 into X. If PA points to a particular element of an array A, then by definition PA plus 1 points to the next element, and in general PA minus I points I elements before PA, and PA plus I points I elements after. Thus, if PA points to A break it 0, asterisk parenthesis PA plus 1 refers to the contents of A break it 1. PA plus I is the address of A break it I, and asterisk parenthesis PA plus I is the contents of I break it I, A break it I. These remarks are true regardless of the type of the variables in the array A. The definition of adding 1 to a pointer, and by extension, all pointer arithmetic, is that the increment is scaled by the size in storage of the object that is pointed to. Thus in PA plus 1, thus in PA plus I is multiplied by the size of the objects that PA points to before being added to PA. The correspondence between indexing and pointer arithmetic is evidently very close. In fact, a reference to an array is converted by the compiler to a pointer to the beginning of the array. The effect is that an array name is a pointer expression. This has quite a few useful implications, since the name of an array is a synonym for the location of the zeroth element. The assignment can also be written as rather more surprising, at least at first sight, in the fact that a reference to A break it I can also be written as asterisk parenthesis A plus I. In evaluating A break it I, C converts it to asterisk parenthesis A plus I immediately. The two forms are completely equivalent. Applying the operator ampersand to both parts of this equivalence, it follows that ampersand A break it I and A plus I are also identical. A plus I is the address of the ith element beyond A. As the other side of this coin, if PA is a pointer, expressions may use it with a subscript. PA break it I is identical to asterisk parenthesis PA plus I. In short, any array and index expression can be written as a pointer and offset, and vice versa. Even in the same statement, there is one difference between an array name and a pointer that must be kept in mind. A pointer is a variable, so PA equal A and PA plus plus are sensible operations. But an array name is a constant, not a variable. Constructions like A equal PA or A plus plus or P equal ampersand A are illegal. When an array name is passed to a function, what is passed is the location of the beginning of the array within the called function. This argument is a variable just like any other variable, and so an array name argument is truly a pointer, that is, a variable containing an address. We can use this fact to write a new version of Strcmp, which computes the length of a string. Incrementing s is perfectly legal. Since it is a pointer variable, s++ has no effect on the character string in the function that called Strcmp, but merely increments Strcmp's private copy of the address as formal parameters in a function definition are exactly equivalent. Which one should be written is determined largely by how expressions will be written in the function. When an array name is passed to a function, the function can at its convenience believe that it has been handed either an array or an pointer, and manipulate it accordingly. It can even use both kinds of operations if it seems appropriate and clear. It is possible to pass part of an array to a function by passing a pointer to the beginning of the subarray. For example, if A is an array and both pass to the function f, the address of element A break it 2 because $A break it 2 and A plus 2 are both pointer expressions that refer to the third element of A within f, the argument declaration can read. So far as f is concerned, the fact that the argument really refers to a part of a large array is of no consequence. 5.4 Address Arithmetic. If P is a pointer, then P++ increments P to point to the next element of whatever kind of object P points to, and P plus equal I increments P to point I elements beyond where it currently does. These and similar constructions are the simplest and most common forms of pointer or address arithmetic. C is consistent and regular in its approach to address arithmetic. Its integration of pointers, arrays, and address arithmetic is one of the major strengths of the language. Let us illustrate some of its properties by writing a rudimentary storage allocator, but useful in spite of its simplicity. There are two routines. Alloc parenthesis m returns a pointer p to n consecutive character positions, which can be used by the caller of alloc for storing characters. Free parenthesis p releases the storage, thus acquired, so it can be later reused. The routines are rudimentary because the calls to free must be made in the opposite order to the calls made on alloc. That is, the storage managed by alloc and free is a stack, or lasting first out list. The standard C library provides analogous functions which have no such restrictions, and in Chapter 8 we will show improved versions as well. In the meantime, however, many applications really only need a trivial alloc to dispense little pieces of storage of unpredictable sizes at unpredictable times. The simplest implementation is to have a log hand out pieces of a large character array, which we will call a logbof. This array is private to alloc and free, since the deal in pointers, not array indices. No other routine need know the name of the array, which can be declared external static, that is, local to the source file containing alloc and free, and invisible outside it. In practical implementations, the array may well not even have a name. It might instead be obtained by asking the operating system for a pointer to some unnamed block of storage. The other information needed is how much of a logbof has been used. We use a pointer to the next free element called allocp. When alloc is asked for n characters, it checks to see if there is enough room left in allocbof. If so, alloc returns the current value of allocp, i.e. the beginning of the free block, then increments it by n to point to the next free error. Free parenthesis p merely sets allocp to p if p is inside allocbof. Like these words, some explanations. In general, a pointer can be initialized just as any other variable can, though normally the only meaningful values are null, discussed below, or an expression involving address of previously defined data of appropriate type. The declaration defines allocp to be a character pointer and initializes it to point to allocbof, which is the next free position when the program starts. This could have also been written. Since the array name is the address of the zeros element, use whichever is more literal. The text checks if there is enough room to satisfy a request for n characters. If there is, the new value of allocp would be at most 1 beyond the end of allocbof. If the request can be satisfied, alloc returns a normal pointer. Notice the declaration of the function itself. If not, alloc must return some signal that no space is left. C guarantees that no pointer that validly points at data will contain 0, so a return value of 0 can be used to signal an abnormal event. In this case, no space, we write null instead of 0. However, to indicate more clearly that this is a special value for a pointer. In general, integers cannot meaningfully be assigned to pointers. 0 is a special case. Tests like show several important facts of pointer arithmetic. First, pointers may be compared under certain circumstances. If P and Q point to members of the same array, then relations like less than and greater than or equal, etc. work properly. It's true. P less than Q is true, for example, if P points to an earlier member of the array that then does Q, the relations equal and exclusive equal also work. Any pointer can be meaningfully compared for equality or inequality with null, but all bets are off if you do arithmetic or comparisons with pointers pointing to different arrays. If you're lucky, you'll get obvious nonsense on all machines. If you're unlucky, your code will work on one machine but collapse mysteriously on another. Second, we have already observed that a pointer and an integer may be added or subtracted. The construction p plus n means the nth object beyond the one p currently points to. This is true regardless of the kind of object p is declared to point at. The compiler scales m according to the size of the objects p points to, which is determined by the declaration of p. For example, on the PDP-11, the scale factors are 1 for char, 2 for int and short, 4 for long and float, and 8 for double. Pointer subtraction is also valid. If p and q point to members of the same array, p minus q is the number of elements between p and q. This fact can be used to write yet another version of Strcmp. In its declaration, p is initialized to s, that is, to point to the first character. In the while loop, each character in turn is examined until the \n at the end is seen. Since \n 0 is 0, and since while tests only whether the expression is 0, it is possible to omit the explicit test, and such loops are often written as: because p points to characters, p++ advances p to the next character each time, and p minus s gives the number of characters advanced over. That is, the string length pointer arithmetic is consistent. If we had been dealing with floats which occupy more storage than chars, and if p were a pointer to float, p++ would advance to the next float. Thus we could write another version of a log which maintains, let us say, floats instead of chars, merely by changing char to float throughout a log and free. All the pointer manipulations automatically take into account the size of object pointed to, so nothing else has to be altered other than the operations mentioned here, adding or subtracting a pointer and an integer, subtracting or comparing two pointers. All other pointer arithmetic is illegal. It is not permitted to add two pointers, or to multiply or divide or shift or mask them, or to add float or double to them. 5.5 character pointers and functions. A string constant written as I'm a string is an array of characters. In the internal representation, the compiler terminates the array with the character \0 so that programs can find the end. The length in storage is thus one more than the number of characters between the double quotes. Perhaps the most common occurrence of string constants is as arguments to functions, as in printf hello world. When a character string like this appears in a program, access to it is through a character pointer. What printf receives is a pointer to the character array. Character arrays, of course, need not be function arguments. If message is declared as char message, then the statement message equal now is the time. Assigns to message a pointer to the actual characters. This is not a string copy. Only pointers are involved. C does not provide any operators for processing an entire string of characters as a unit. We will illustrate more aspects of pointers and arrays by studying two useful functions from the standard International library to be discussed in Chapter 7. The first function is Strcmp. The first function is Strcmp. The first function is Strcmp, parenthesis s, comma t, which copies the string t to the string s. The arguments are written in this order by analogy to assignment, where one would say s equal to assign t to s. The array version is first. For contrast, here is a version of Strcmp with pointers, because arguments are passed by value. Strcmp can use s and t in any way it pleases. Here they are conveniently initialized pointers which are marched along the arrays a character at a time until the \0, which terminates t, has been copied to s. In practice, Strcmp would not be written as we showed it above. A second possibility might be this moves the increment of s and t into the test part. The value of *t++ is the character that t pointed to before t was incremented. The postfix ++ doesn't change t until after this character has been fetched. The same way, the character is stored into the old s position before s is incremented. This character is also the value that is compared against \0 to control the loop. The net effect is that characters are copied from t to s up to and including the terminating \0. As a final abbreviation, we again observe that a comparison against \0 is redundant, so the function is often written as like this. Although this may seem cryptic at first sight, the notational convenience is considerable, and the idiom should be mastered, if for no other reason than that you will see it frequently in C programs. The second routine is Strcmp. What the fuck is this? The second routine is Strcmp, parenthesis st, which compares the character strings s and t and returns -0 or positive according as s is lexicographically less than equal to or greater than t. The value returned is obtained by subtracting the characters at the first position where s and t disagree. The pointer version of Strcmp. Since plus plus and minus minus are either prefix or postfix operators, other combinations of asterisk and plus plus and minus minus occur, although less frequently. For example, asterisk plus plus p increments p before fetching the character that p points to. Asterisk minus minus p decrements p first. Exercise 5 middle score 2. Write a pointer version of the function Strcmp, which we showed in chapter 2. Strcmp parenthesis st copies the string t to the end of s. Exercise 5 middle score 3. Write a macro for Strcmp. Exercise 5 middle score 4. Rewrite appropriate programs from earlier chapters and exercises with pointers instead of array indexing. Good possibilities include getLine, chapter 1 and 4, A to I to A, and their variants, chapter 2, 3 and 4, refers, chapter 3, and index, and GetUp, chapter 4. 5.6 pointers are not integers. You may notice in older C programs a rather cavalier attitude toward copying pointers. It has generally been true that on most machines, a pointer may be assigned to an integer and back again without changing it, and back again without changing it. No scaling or conversion takes place, and no bits are lost. Regrettably, this has led to the taking of liberties with routines that return pointers which are then merely passed to other routines. The requisite pointer declarations are often left out. For example, consider the function Strcmp parenthesis s, which copies the string s into a safe place, obtained by a call on a log, and returns a pointer to it. Properly, this should be written as. In practice, there would be a strong tendency to omit declarations. This will work on many machines, since the default type for functions and arguments in it is int and int, and pointers can usually be safely assigned back and forth. Nevertheless, this kind of code is inherently risk, for it depends on details of implementation and machine architecture which may not hold for the particular compiler you use. It's wiser to be complete in all declarations. The program named will warn of such constructions in case they creep in inadvertently. 5.7 Multi-dimensional arrays. C provides for rectangular multi-dimensional arrays, although in practice they tend to be much less used than arrays of pointers. In this section, we will show some of their properties. Consider the problem of date conversion from day of the month to day of the year and vice versa. For example, March 1 is the 60th day of a non-leap year and the 61st day of a leap year. Let us define two functions to do the conversions. Day of the year converts the month and the day into the day of the year. The month day converts the day of the year into the month and day. Since this later function returns two values, the month and day arguments will be pointers. Set M to 3 and D to 1, March is first. These functions both need the same information, a table of the number of days in each month. 30 days has September. Since the number of days per month differs for leap years and non-leap years, it's easier to separate them into two rows of a two-dimensional array than try to keep track of what happens to February during computation. The array and the functions for performing the transformations are as follows. Like this. The array day underscore tab has to be external to both day underscore of underscore year and month underscore day, so they can both use it. Day underscore tab is the first two-dimensional array we have dealt with in C. By definition, a two-dimensional array is really a one-dimensional array, each of whose elements is an array, hence subscripts are written as rather than as in most languages. Other than this, a two-dimensional array can be treated in much the same way as in other languages. Elements are sorted by rows, that is, the rightmost subscript varies vested as elements are accessed in storage order. An array is initialized by a list of initializers in braces. Each row of a two-dimensional array is initialized by a corresponding sublist. We start the array day underscore tab with a column of 0 so that month numbers can run from the natural 1 to 12 instead of 0 to 11. Since space is not at a premium here, this is easier than adjusting indices. If a two-dimensional array is to be passed to a function, the argument declaration in the function must include the column dimension. The row dimension is irrelevant, since what is passed is, as before, a pointer. In this particular case, it is a pointer to objects which are arrays of certain ends. Thus, if the array day underscore tab is to be passed to a function f, the declaration of f would be like this. The argument declaration in f could also be like this. Since the number of rows is irrelevant, or it could be like this, which says that the argument is a pointer to an array of certain integers. The parentheses are necessary since brackets have higher precedence than asterisk. Without parentheses, the declaration like this is an array of certain pointers to integers, as we shall see in the next section. 5.8 Pointer arrays, pointers to pointers. Since pointers are variables themselves, you may expect that there would be uses for arrays of pointers. This is indeed the case. Let us illustrate by writing a program that will sort a set of text lines into alphabetic order. A stripped down version of the Unix utility sort. In chapter 3, we presented a shell sort function that would sort an array of integers. The same algorithm will work, except that now we have to deal with lines of text, which are of different lengths, and which, unlike integers, can't be compared or moved in a single operation. We need a data representation that will cope efficiently and conveniently with variable length text lines. This is where the array of pointers enters. If the lines to be sorted are stored end-to-end in one long character array, maintained by a log, perhaps, then each line can be accessed by a pointer to its first character. The pointers themselves can be stored in an array. Two lines can be compared by passing their pointers to Strcmp. When two out-of-order lines have to be exchanged, the pointers in the pointer array are exchanged, not the text line themselves. Not the text lines themselves. This eliminates the twin problems of complicated storage management and high overhead that would go with moving the actual lines. The sorting progress involves 3 steps, like this. Read all the lines of input, sort them, print them in order. As usual, it is best to divide the program into functions that match this natural division, with the main routine controlling things. Let us defer the sorting step for a moment and concentrate on the data structure and the input and output. The input routine has to collect and save the characters of each line and put an array of pointers to the lines. And we also have to count the number of input lines, since that information is needed for sorting and printing. Since the input function can only cope with a finite number of input lines, it can return some illegal line count like -1 if too much input is presented. The output routine only has to print the lines in the order in which they appear in the array of pointers. The new line at the end of each line is deleted, so it will not affect the order in which the lines are sorted. Like this, the main new thing is the declaration for line PTR. Says that line PTR is an array of lines elements, each element of which is a pointer to a char. That is, line PTR bracket I is a character pointer, and asterisk line PTR bracket I accesses a character. Since line PTR is itself an array which is passed to right lines, it can be treated as a pointer in exactly the same manner as our earlier examples, and the function can be written instead as asterisk line PTR points initially to the first line. Each increment advances it to the next line while n lines is counted down. With input and output under control, we can proceed to sorting. The shear sort from Chapter 3 needs minor changes. The declarations have to be modified and the comparison operation must be moved into a separate function. The basic algorithm remains the same, which gives us some confidence that it will still work. Since any individual element of V, alias line PTR, is a character pointer, TMP also should be, so one can be copied to the other. We wrote the program about as straightforwardly as possible, so as to get it working quickly. It might be faster, for instance, to copy the incoming lines directly into an array maintained by read lines, rather than copying them into line and then to a hidden place maintained by a log. But it's wiser to make the first draft something easy to understand, and worrying about efficiency later. The way to make this program significantly faster is probably not by avoiding unnecessary copy of the input lines, replacing the shear sort by something better, like quick sort. It's more likely to make a difference. In Chapter 1, we pointed out that because while and for loops test the termination condition before executing the loop body even once, they help to ensure that programs will work at their boundaries. In particular, with no input, it is illuminating to walk through the functions of the sorting program, checking what happens if there is no input text at all. Exercise 5, middle score 5. Rewrite red lines to create lines in an array supplied by main rather than calling a log to maintain storage. How much faster is the program? 5.9 Initialization of pointer arrays. Consider the problem of writing a function month underscore name parenthesis n, which returns a pointer to a character string containing the name of the nth month. This is an ideal application for an internal static array. Month underscore name contains a private array of character strings and returns a pointer to the proper one called. The topics of this section is how that array of names is initialized. The syntax is quite similar to previous initializations, like this. The declaration of name, which is an array of character pointers, is the same as line ptr in the sorting example. The initializer is simply a list of character strings. Each is assigned to the corresponding position in the array. More precisely, the characters of the ith string are placed somewhere else, and a pointer to them is stored in name bracket I. Since the size of the array name is not specified, the compiler itself counts the initializers and fills in the correct number. 5.10 Pointers vs multi-dimensional arrays. Newcomers to C are sometimes confused about the difference between a two-dimensional array and an array of pointers, such as name in the example above. Given the declarations, the usage of A and B may be similar in that A, like this, are both illegal references to a single int. But A is a true array. All 100 storage cells have been allocated, and the conventional rectangular subscript calculation is done to find any given element. For B, however, the declaration only allocates 10 pointers. Each must be set to point to an array of integers. Assuming that each does point to an 10-element array, then there will be 100 storage cells set aside, plus the 10 cells for the pointers. Thus, the array of pointers uses slightly more space and may require an explicit initialization step, but it has two advantages. Accessing an element is done by indirection through a pointer rather than by a multiplication and an addition. And the rows of the array may be of different lengths. That is, each element of B need not point to a 10-element vector. Some may point to 2 elements, some to 20, and some to none at all. Although we have phrased this discussion in terms of integers, by far the most frequent use of arrays of pointers is like that shown in month_name to store character strings of diverse lengths. Exercise 5 middle score 6. Rewrite the routines day _of_year and month_day with pointers instead of indexing. 5.11 Command line arguments. In environments that support C, there is a way to pass command line arguments or parameters to a program when it begins executing. When the main is called to begin execution, it is called with 2 arguments. The first, conventionally called argc, is the number of command line arguments the program was invoked with. The second, argv, is a pointer to an array of character strings that contain the arguments, 1 per string. Manipulating these character strings is a common use of multiple levels of pointers. The simplest illustration of the necessary declarations and use is the program equal equal, which simply equals is command line arguments on a single line separated by blanks. That is, if the command equal hello world is given, the output is hello world. By convention, argv bracket 0 is the name by which the program was invoked. So argc is at least 1. In the example above, argc3 and argv bracket 0, argv bracket 1, and argv bracket 2 are equal, hello, and word, respectively. The first real argument is argv bracket 1, and the last is argv bracket argc minus 1. If argc is 1, there are no command line arguments after the program name. This is shown in equal. Since argv is a pointer to an array of pointers, there are several ways to write this program that involve manipulating the pointer rather than indexing an array. Let us show two variations. Like this. Since argv is a pointer to the beginning of the array of argument strings, incrementing it by 1, parenthesis plus plus argv, make it point at the original argv bracket 1 instead of argv bracket 0. Each successful increment moves it along to the next argument. Asterisk argv is then the pointer to that argument. At the same time, argc is decremented when it becomes 0. There are no arguments left to print. Alternatively, this version shows that the format argument of printf can be an expression just like any of the others. This usage is not very frequent, but worthy remembering. Okay, guys. It is time for me to take a break. See ya.